Okay, guys, hello everyone. So let us start our lecture. It's Friday, November 6th, and please take it seriously. We have many things to do today. I recall your exam 3 is just in 2 weeks from now. It will be Friday, November 20th. So I do encourage you to be ready, and not much time left, and we still have to do homework before. Regarding homework, before proceed, I want to share my screen with you and show you something, like I did before. So if you see my screen now, you will see here it is. So what you will see now on my screen, it's again, I plot diagram when I have exams versus homeworks. So here you have, actually, here is average over all 5 homeworks. It's not over 3 over all 5 homeworks as this axis, and this axis is average of your 2 exams. So what do I want to tell you based on this? I do want to tell you that you should do your homework and do it yourself. You may clearly see there is really good, if you consider this diagonal, there is really good correlation between your homeworks and your exams. Well, somebody managed to write exam without homeworks, somebody fails in spite of homeworks, but most likely they do correlate. So please realize, even homeworks don't cost much. It's only 10 points of your cumulative score. It's very helpful for your exam. Exams are important and you must do it. You have your homework number 6, which is posted now, right? It will be due Wednesday. On Monday and Tuesday, you will have your help session. So please use this. It really helps. I know some people understand that it would be helpful after it. So please take it timely. And I do believe after lecture today, you should be able to do your entire homework. I do believe in this. Now, so let's proceed. So what is our current stage? So I recall we went through part A of the slides. So I believe what you see on the screen now, it's more or less trivial for you. You know power cycle and refrigeration cycle and heat pump cycle. You know second basics of second law, at least you think you know. You know Calvin Planck and Clausius statements, right? So basically, I would say we qualified second law. So you know what it is about and what may happen, what not. Now our next step is to quantify it, to measure it somehow. So what second law means in terms of numbers? So I tell you that many devices that we considered before may not exist in practice. They may not exist because of second law. So what we are going to do now, we should quantify it somehow. So how, based on some data, some numbers, you may give an answer. Does it exist or not? Is it possible or it's not possible? That's what we are going to do. And everything is self-consistent. So please remember, last time we started chapter B, and that's actually what we are going to do. And we will talk about, and we start talking about irreversibilities. So you know that what is reversible? It's straightforward. Process is reversible if it can go in both directions. Otherwise, it's irreversible. When you transfer heat into work, it's irreversible. When you melt a brick of sugar into sweet tea, in sweet water, because or tea, you make it sweet, it's irreversible. When you mix oxygen and nitrogen and create air, it's irreversible. You cannot easily get it back. These are, so most of the process we have, actually all the realistic process we have, are entirely irreversible. So our next point will be how to measure irreversibilities, how to say what is more irreversible and less irreversible, what is better, what is worse. Because you know, in fact, irreversibilities, it's penalty you pay according to second law. So we want to measure, is it big penalty or small penalty? That's what we're going to do. So that's what we started last time, right? We discussed it, and basically we realized that, in fact, all we face in nature, all the processes we face in nature, unless some simplified, are irreversible. So unless you talk about frictionless pendulum like this, unless you talk about quasi-equilibrium expansion of compression gas back and forward, other things are irreversible. So what are irreversibilities? I think we described last time. So heat transfers through a finite difference temperature, right? Because energy has a quality. Higher temperature gives higher quality of energy. Unstraight expansion of a gas. spontaneous chemical reaction, because it cannot, chemical reaction goes in one direction. Like I discussed, mixing, friction, which causes dissipation, elastic deformation when I cut something. These are irreversible processes. All these processes generate entropy. And we will talk about this in next chapter, next week. Since, actually in 2 weeks from now, since you can generate entropy, you cannot destroy it. So it can go only in one direction, from past into the future, right? So now, basically, what we talk about? We talk that if there are irreversibilities, process is irreversible. Now, what we want to do? We will distinguish internally reversible and externally reversible processes, okay? We will distinguish them. What does it mean for us? And I think I started describing this last week, but let me continue on it. So, yes, in the nature, there is no real reversible situations. You go in past into the future. You cannot go to previous. But if you have a system and zoom in the system, something which happens inside may look like reversible. And here is the example. So let's consider example like this. Let's say I have vessel, like on the screen you see a vessel with water, H2O. And let's say on my left hand, I have fridge. Here it is, okay? And on the right hand, I have appliance, electrical appliance, stove. And I will do the following. I will take this vessel with water, this tank. I will put on the fridge first. What will happen? Fridge will cool it, right? And it will get frozen. It will be liquid phase and then solid phase. Then I will take it from my fridge and put on appliance. What will happen on appliance? Yes, I will submit heat there. Heat will go latent temperature, so it will melt, then evaporate, and eventually will have superheated phase. Right? We discussed many times. It's trivial. Then I will take it from appliance and put it back into fridge. It will get cold, right? Then I will put back to appliance. Okay, what I'm doing? How many times may I do it? All our lecture I can spend making this. So let me say, is this process reversible or not? It's a tricky question. Who thinks it's reversible? Who thinks it's not? Yeah, people answering this. Exactly. Some people say not. Yeah, why not? And that's true. Why not? Because like, in fact, what happening here, I'm wasting time and I'm wasting the lecture. If all my lecture, I will go from fridge to appliance and back, definitely, I waste your time. I will never have this lecture back. I will never have Friday 11 o'clock again. I wasted this time. I cannot put it back. I cannot go from 12 o'clock back to 11. And in terms of why it's irreversible, because we generate irreversibilities. You have a fridge, right? Your fridge works. Your fridge consumes electricity, right? You can never get it back. So your appliance also consumes some source of energy, maybe electricity, maybe gas, whatever it is. But again, you burn gas to heat this water. You cannot get heat from this water and put it back into the gas. You cannot burn gas back, right? So it's really irreversible. So it's an irreversible process. But now assume that I am not, you consider this problem not from my point of view and not from your point of view. Assume that you are a molecule of water, H2O molecule, which sits in this tank, okay? Remember, molecules are the same. Molecule of ice, molecule of vapor, molecule of liquid is the same. The key point is collective motion, what faces it. So imagine that you are such a molecule. So let's describe this picture from the point of view of this molecule. What happens? From this point of view of molecules, you go back and forward, right? You got crystallized, you're part of crystal, then you have neighbors in a liquid phase, then you become vapor, then you become ideal gas, and then go back and forward, right? So if you're a molecule which never leaves this tank, all the life looks like back and forward, right? Do you agree? So from my point of view, definitely I know the time is expensive and energy is expensive. This really, irreversible scenario. From the point of view of that molecule, it's reversible. Molecule has no idea about appliance, and molecule has no idea about stove. Molecule has idea only about what happens with it. So this is internally reversible process, okay? For your system of liquid here, for your system of the liquid vapor system, whatever, this is internally reversible. Do you understand? Does it make sense for you? So, and why it's important? Because this process may exist in reality. Sometimes they exist. You cannot have fully reversible process, but you can create a system inside which, like a pendulum, you will have internally reversible environment. So this process may exist, and you will deal with it. From the point of view of water, no entropy is generated. Entropy goes around it. So that is means that there are no internal irreversibilities in such a system that you see, right? Because inside internal inner structure of the system, internal part of the system does not know about stove, does not know about fridge. It just lives itself. So it means that in such a system you have only external irreversibilities. Does it make sense? I hope so. That it is. So basically that's what we should distinguish in totally reversible process when there are no irreversibilities either in the system in surrounding, externally reversible when there are no irreversibilities outside it, and internally reversible when there are no irreversibilities only inside the system. It can be outside, and this process may exist. And this will be ethanol for us. Why we talk about this? Why we talk about internal reversibility? Why we talk about reversible process at all if they don't exist? Because this is your measure. This is some ethanol. This is some ethanol for you, right? Like people say, everyone try to be best. You talk about saint people, right? Sometimes, well, it's religious questions. I don't want to touch it, but anyway, you want to be the best, right? But there is idea that actually you cannot be saint, right? You do something bad, but saint person is some ethanol that you want to attain, right? You are worse, but why you talk about saint people? Because this is somebody you want to look like. You try to approach this level, correct? And depending on how far you from that level, we can say you're a good person or bad person or terrible or whatever, right? So why do we talk about this? Now our next stage to see how far you are from that saint person, how far you are from internally reversible scenario. The closer to you are to it, the less irreversibilities are, the better efficiency you have, the less entropy generated, the less penalty you pay according to second, right? But what is key point that you cannot be better than the same person, right? It's your ethanol. So what we do now, when we consider real device, we will say, okay, how it would work if it was reversible? Say how it would work if it was internally reversible. And then you compare your device, your cycle, your system with such idealized system. And that's based on this, you can make conclusion. If your system is worse than idealized, later we'll say what does it mean worse. If it's worse, okay, that's feasible, that may exist in reality, it's okay. If your calculations show that your system is identical to idealized, what you can say? It's hard to believe, but potentially this may happen. You cannot decline it based on second law. But if your system appears better than idealized, then I can tell you something is wrong with you. It cannot happen. I don't know why. I don't care what you did wrong. I don't know how you miscount, but it's wrong. According to second law. If you were right, we would not sit here. If you were right, Big Bang would not happen. Universe would not exist. Does it make sense for you? So how do you measure it now? So do you agree? It can be, we will prove it, but do you even like on naive level, just mentally, semantically, you may agree, you may feel that reversible cycle is better than irreversible as long as they operate between the same two reservoirs. Do you agree? Right? If I potentially, so if I have, let's say I have the same reservoirs, I have temperature TH here, and I have temperature TL here. Let them be in Kelvin. And I have two cycles. Let's say I have one heat engine, and I have some kind of ideal heat engine, okay? Ideal, okay? Ideal. So do you agree that my heat engine is worse, it's not better than that one? It will be always like this? Can you believe in this? Right? Okay. If you believe in this, that's our next scenario. You know, there is a classical phrase that all, from classics, that all happy families are happy identically, are happy in the same manner. All unhappy families have their own troubles, are unhappy in their own way, right? Why I say this? Because it's exactly what we're talking here. Presumably, there are no absolutely happy families, but this is, maybe it's not my family or your family, but this is our ideal. That is our etalon. That's how we would like to look like. I want to have ideal family. And I know that this ideal family will be best for me. So even if it does not exist, I want to be compared to it. And I know that all ideal families would be identical. They're all happy in the same way. They're all the best. They have the same efficiency. And all are realistic families that we may have are worse than such an ideal family. Do you understand this? Let me say in words of thermodynamics. Do you agree that as soon as I have these two reservoirs, like we plotted here, if I have the same, we talk about the same reservoirs, and since we talk about the same reservoirs, like this, only two reservoirs, that, and I may have many, many various heat engines which would operate between these reservoirs, correct? So do you agree from this statement that all ideal all ideal engines, it means that all internally reversible engines operating here will have the same efficiency. And this efficiency will be maximal. And this efficiency will depend only on what? On TH and TL, or more exactly of the ratio, because there is no other way to measure reservoir. While all realistic heat engines will be worse. They will have efficiency less than the ideal one, right? Do you agree? That's what I say here. And what is stated here is what we call Carnot principle or Carnot corollaries. It stated that the thermal efficiency of an irreversible power cycle is always less than respective reversible cycle, provided they operate between the same two reservoirs. And all reversible power cycles operating between the same reservoirs have the same thermal efficiency. It will be maximal efficiency that can be attained, right? Otherwise, I can say that you remember we talk about thermal efficiency. Thermal efficiency should go from 0 to 100%, right? To 1. Correct? But now I can say that it should be no larger than some maximal efficiency, which is less than 1, right? And that gives you second law. You cannot have 100% efficiency. You have second reservoir. You should lose some heat. You should pay some penalty. That's how you pay. And this maximal value, it will depend on temperatures only. Actually, on two temperatures, TH and TL. Why? Because reservoirs don't know about pressure or other parameters. They know only about temperature. All happy family, happy in the same manner. All unhappy, unhappy in different manners. If you want to know how far you're from happiness, find one unhappy family and see how they're happy. Does it make sense? Okay. So, can we prove it mathematically? Yes, we can. Even you believe in this, we can prove. And again, you can prove it like we did typically with, like we're doing like in school algebra or geometry, because it's a mathematical approach. Like remember how we prove theorems. If you in a theorem, you have a statement, and if you want to prove it, what you say? Assume some opposite. Assume this statement is wrong. Assume opposite statement. And then come to some contradiction, come to some nonsense. And if you come to this nonsense, it will mean that contradict, your opposite statement was wrong, so your theorem is proven. Remember it from school? That's actually how we proved that Kelvin Planck and Clausius statements are identical. We proved, right? Remember, we assume that you can violate Kelvin Planck, and you come to the statement that then you violate Clausius, and vice versa. So let's do the same here. So let's say, now I will say with formulas exactly that I did in words. So I have two reservoirs with temperature TH and TL. And let's say what I have here. Let's say I have irreversible heat engine, number 1. And I have two reversible heat engines, 2 and 3. And I want to prove that engines 2 and 3 have the same efficiency, which will be larger than that of first one. You already believe in this, talking about happy and unhappy families, but let's do it mathematically. So how we will do it? Let me say the following. Let's assume that my statement is wrong. Let's say that my irreversible cycle, has better efficiency than my reversible cycle. Let me assume it. So what, and let's check if it's true or not. What do we know about reversible cycles? Reversible, it's reversible because it can go backward, right? So reversible cycle, instead of transferring heat into work, it can actually convert work into heat and put backward. So let me combine system 1 and 2 together. So heat goes here to cycle 1, part of it is converted and into work, and part is released. And now what I do here, I use this second reservoir, I use a second heat engine, sorry, to get heat from cold reservoirs and put it up. If I can, let me now zoom it and consider the system together. What will I have? I will simply have that now, since I assume that my efficiency 1 is better than efficiency 2, here I can convert more heat into work than submitted here. So I will be able to transfer heat into work entirely without releasing something down. That is nonsense. Why? Because it violates Kelvin Planck statement. Do you agree? So it's wrong. It cannot happen. So my reversible cycle is definitely worse than reversible. Now, but maybe there is no magic numbers here. Maybe there are two reversible cycles, number 2 and number 3, and they have different efficiencies, right? And may I believe in this? Okay, let's check. Assume it's the case. The same story. Let me do the following. Then let me put cycle 3 backward, and I will have reversible in here. And now I will see the following. What system together does? It will fridge, which transfer heat from cold to hot source. It will happen that if 3 is better than 2, then I can transfer heat directly here without work input, which is violation, classical violation of Clausius statement. Maybe it's vice versa. Maybe 2 is larger than 3. Okay, let's change the size and put it, one is backward, one is forward. Again, I violate. Based on this, I come to this conclusion that all happy families are identical. You cannot distinguish them. They all reversible cycles operating between the same thermal reservoirs will have the same efficiency. Do you understand this? Please ask me something. I know it's a lot of philosophy, a lot of words, and less math and less physics here yet. It will come soon. So what we concluded. Sorry if I repeated too many times, but I want you to get it, because we will live with this statement until the end of semester. If you understand, great. If not, it's time to pick up. So if I want to know, so how can I know, do I have happy family or not? If I know that all happy families are identical and all unhappy are worse than happy. Based on this, it's enough for me to find one happy family, go to visit them and compare them to me, to us. And if they're better than me, I will say, okay, I am not ideal. And if they're equal to me, I say, you know, great, I am ideal. And if I am better than them, that something goes wrong with me, I miscounted. Okay? So it's enough to find one ideal family to make this conclusion. Right? Okay. So how to do second law analysis here? How to check? And if you have reversible, irreversible, possible or impossible cycle. So find one ideal cycle operating at the same reservoirs, at the same conditions. Find one cycle, only one, it's enough. And then you will know that all other cycles, all other cycles will be not better. All other cycles will have the same efficiency if they're ideal, and they will have less efficiency if they're not ideal. Do you understand? So now I should see example of one particular cycle which would be ideal. And I know it. This is Carnot cycle. Now, from this point, if you not hearing me or whatever, it's a very good time to wake up and remember Carnot cycle. It's really important. This example of internally reversible cycle, Carnot cycle, how it does. And this cycle operates between two reservoirs and in internal reversible manner. And what you should know about it, why we can talk about Carnot cycle. This is the simplest cycle operating as this environment. And that's how it looks like. Here we talk about power cycle. When it goes clockwise, if it goes counterclockwise, it will be reversible Carnot cycle, you will realize. So now that's something important. This cycle consists of two adiabats and two isotherms. So you must remember how it look like, this PV diagram look like, you must remember this. If you somebody wake you up overnight in the 3 o'clock in the morning, you say, what is Carnot cycle? You should say two isotherms, two adiabats. You must remember. Does it make sense? So here how it looks like. Again, you can start from any point, but ideally it's like this. You go from point 1 to point 2. And this is isotherm. Temperature is constant here, okay? Here is isothermal expansion. Heat is submitted here. Okay, that's how heat goes from hot reservoir to into your system. And something is converted into work. Then you don't heat it anymore. So and you take your source of heat out, okay? You take source of heat out, and from state 2 to state 3, it will intrinsically proceed expanding. There will be no heat transfer here. So this is adiabatic process, adiabatic, okay? So here there is no heat transfer, okay? It's just adiabatic process. Now, then it stops, and in state 3, you connect your system, you cool your system, you put it on fridge, and then heat will go out. This is your cold reservoir. So here it was your hot reservoir, here is your cold reservoir. You go from 3 to 4, and you cool it, right? And it's isothermal cooling. This heat will go out. And you may also realize that here work will be done on this. And eventually at state 4, you take out your cooling, and again it will intrinsically shrink until you go to point 5. And here it will be adiabatic compression. No heat transfer here again. So adiabatic, let's see. Isothermal expansion, adiabatic expansion. In 1, 2, and 2, 3, work is positive. It's done by the system. It is released. Do you understand? 3, 4, and 4, 1, it will be compression. So work will be done on the system. And work over the cycle, it will be what you see crossed here in this picture, right? It's work over the cycle here. Work up, right? So you may realize from here that heat QH goes in, QL goes out, and you may clearly see that what is this work? It will be QH minus QL. Do you understand this? So QH minus QL give you work over the cycle, how they call it, network, right? Do you agree with me? And what will be efficiency of the cycle? Your efficiency will be what is desired, like for any heat engine, or what is required, correct? So what will be your efficiency? Your efficiency will be what is desired. Desired work output, so it will be this work over cycle network. What is required? It is QH, Q in with required. Remember last lecture, right? And basically it will be what? It will be also QH minus QL divided by QH. That is your efficiency. As you see here, you have 4 variables and 2 equations. You need something else to identify everything. But what you know here, that we talk about Carnot cycle. So this value, if we talk about Carnot, it should be function of what? It should be function of temperatures only, TL and TK. Do you understand this? So that is Carnot cycle. Why do we talk about Carnot cycle? What is magic number about Carnot cycle? Why we need Carnot cycle? Because this is simplest internal reversible cycle we may have. We may have others, but they will be more complicated. So we start this. And it's enough to consider one, because what I can say from here. Do you agree that if I find the efficiency of this Carnot cycle, if I find this efficiency, then all other cycles operating between these reservoirs will have the same efficiency. And all realistic cycles operating here will have less efficiency, like we discussed in previous slide. Do you understand this? And I will find efficiency. That's what we are going to do. But does it make sense first? Please ask if something wrong. How it goes again, you may take a look here if you want. Basically, that's what we have. If you may consider, I can actually. Here on small scale here. Yes, it will be nice to see. So basically, that's what we have. So what do we have here in such a Carnot cycle? First, we have heat additions to the system, right? Reversible isothermal expansion. Heat goes in, piston goes like this. Then you have reversible adiabatic expansion here. Reversible isothermal expansion. And eventually reversible adiabatic compression. All there here. Do you understand? Why it's reversible? Because it's because remember, is heat conversion into work, heat transfer through finite temperature is irreversible. In this way, we have reversible. You can go from 1 to 2 and from 2 to 1. You can go from 2 to 3 and to 3 to 1, whatever it is. When you go clockwise, your work will release. When you go counterclockwise, the work is consumed. That's actually what you may see here. You may realize let's compare these two pictures. Picture on the left shows direct Carnot cycle, its power cycle, its heat engine. What we see in picture on the left. QH here is converted into work, but you cannot convert it entirely, so some heat is released here, right? But since it's reversible, I can push it counterclockwise. And if I go do you understand this? Here is clockwise. This is clockwise. So this is positive, and this is counterclockwise. What does it mean that I go counterclockwise? If I go counterclockwise, and this in the left-hand side, work goes out, right? Work out. And it's positive. But here, if I go counterclockwise, work will be negative. Work will be input here into my system. So my work take QL from here and submit QH upstairs. Do you understand this? So this will be refrigeration or heat pump cycle, whatever you use it. Do you agree with me? I hope so. That it is. So basically, again, how it looks like in PV diagram. And basically, what we want to get from, oh, sorry, it flies here. You get from here. Your next point will be to clarify what is efficiency, how to calculate what is the efficiency of Carnot cycle, right? If you can calculate this efficiency, it's done, you know everything. Do you agree with me? So, how to calculate? Typically, when I teach in person class, I typically derive it on my screen. It takes some time, but now I don't want to waste your time. It's limited, we have short semester, and I want to give you some other points. So I ask you the following. Please derive, and if you want to get one bonus point, please derive efficiency of Carnot cycle for ideal gas operating between temperature TA, TH, and TL. But you should understand how it goes. I will check carefully. So you should derive it. And I know that you can Google and find it in many ways, in many books, in many places, but I will check if you understand it or not. Its derivation should be very careful without gaps. If there are gaps, it means that you don't understand. What you can do here, please consider ideal gas. It's enough to consider ideal gas and write down equation for the process 1, 2, 2, 3, 3, 4, and 4, 1. How to write this equation? You know these equations, right? For process 1, 2, it will be what? It will be PV is equal to constant, and it will be MRTH, correct? The same you can write for process 3 and 4. It will be the same. PV will be constant. It will be MRTL. For processes 2, 3, and for processes 1, 4, what do we know? It's a diabatic process. So it will be PV to the power K is constant, where K is Cp over Cv. It's a diabatic exponent, right? That's what we'll get. That gives the relation between 1, 2, 3, and 4. And then you can find how you'll find your efficiency. Again, you can write, let's say you deal with closed system. Why? Because you select simplify Carnot cycles. Let's take a closed system. You will have that what? You will have the delta U, for instance, for process 1, 2. It will be what? It will be Q1, 2 minus work 1, 2. And this value will be 0, right? Because temperature is the same, so they relate. The same equation you will be able to write for stage 3, process 3, 4, 3 and 4. You combine them. You will find the same relation. You know how boundary work look like? It will be PV logarithm T2 over T1, right? Or V2 over V1, their output, right? We just finished chapter 4, you remember this. And then you will find your efficiency. What will be your efficiency? Your efficiency will be QH minus QL divided over QH. Okay? Do you understand this? But then, if you calculate everything as I told you, if you calculate it properly, and I want you to do it, then, guys, you will come to very nice expression. It will be TH minus TL over TH, because this particular Carnot cycle. That it is, and that is your final formula. Now you know that efficiency of Carnot cycle looks like this. I do request you try to derive it. Some people ask more, you say that you don't have enough bonuses in the class, that will be your bonus if you solve. But that's something that you should derive it, and I want you to remember. That is your formula. Efficiency of a Carnot heat engines is like this. It's very simple. It's simple to remember. Just instead of TH, instead of QH and QL, instead of Q in and Q out, write TH and TL. That's it. Okay? But if it's like this, what does it mean? Now I know that all other cycles that I have cannot exceed this efficiency. This is maximal efficiency that I may ever attain. If my TH is 1000 Kelvin and TL is 600 Kelvin, my efficiency here will be 60%. And from here, it will mean what? That I cannot exceed it. I may never exceed it. It can be only less. That it is. So basically, now, what is your analysis? I can say that any efficiencies that I may have, it will be what? It will be QH minus QL over QH, right? For any cycle, it will be no larger than TH minus TL over TH. And this in turn is larger than 1, right? Because it can, yeah, good comment, good point. These temperatures should be in Kelvin, okay, or in Rankine, but it should be from absolute 0. And you may realize now, if your TL tends to absolute 0, you may theoretically approach 100%. But that's maximum that you can attain. Your efficiency cannot be here. If your efficiency is here, our universe would not exist. That's a must. That's a key point to understand. Do you understand this? So that is your strategy now. That's how you're going to solve all the problems. Find your efficiency. Find maximal efficiency. That is Carnot efficiency, whatever you call it. And then compare. What you may have? You may have that your efficiency is less than Carnot efficiency. It may be equal, or you can get that it's larger. If your efficiency is less than this efficiency, what can you say from here? It's okay. It's possible, right? It's possible. It's possible and reverse. It's your system is irreversible. So you have irreversible system. Correct? If your efficiency occasionally appears like this, what can you say from here? You may say that it's theoretically possible. It means that you deal with a reversible cycle. So your cycle is Carnot cycle. May it happen? I would not invest money in this because it happens seldom, but you cannot decline it. Potentially it can be. Like if I give you exam and you say me, I will get 100 points. Is it true? Well, it will be hard, but I cannot say I don't believe you. I give you F because you're lying. I cannot say this. You may get it. But if you say you will get 105 points, I will say that you don't know math. And this time you don't know thermodynamics. So if you what I mean here, if your efficiency is larger than maximal, then you say it's impossible. It's impossible. Okay, it's impossible. It's impossible not because there are dissipations. Some people confuse. It's not because there are friction. It's not because efficiency is not 100%. It's not possible according to second law. To be possible, you should go backward to Big Bang. Okay? Does it make sense? What this analysis mean? And that's what you have in your homework. So let's do some examples. Let me go through some. Yeah, so that is a good example. So let's do power, that's what we call power cycle analysis or Carnot analysis or second law analysis. So let's read this text body and we proceed. So let's say I have power cycle. It's stated that there is a system which operates between two reservoirs. It receives 100 kilojoules from hot reservoir, like like here. So it receives 100 kilojoules from here. Out of them, it rejects 600 kilojoules here, right? The question is it possible or not? Well, you may say, okay, how can I know this? Here are the hints for you. Here are the temperatures what happen. It stated that your hot reservoir is 500 Kelvin, and there are three options for cold reservoirs, 2, 3, and 400, this one. So that it is. And the question is how it may happen. So what are you doing? What is your strategy? And now please be careful, you employ the strategy for practically all problems we have. So first of all, you say, okay, what is my work output? By the way, it's not known here. From here, you will say that your work will be what? Work will be 1000 minus 600, correct? So it will be 400 kilojoules. You get it from here. And by the way, check. If it's stated in your text that your work will be here 600, if QH and QL don't give you together work output, sometimes again, we don't use TL, we use TC, it depends on the book you have. Then what will happen? It means that you violate first law. If you violate first law, you can violate everything. It does not matter, right? So that it is. So what is your efficiency? Let's calculate it. From here, I can say, what is my efficiency? What is desired and what is required? What I desire? I desire this work output. So it's 400. What is required? Required 1000, right? So my efficiency is 40%, 0.4. And what I will do next? Now I will find Carnot efficiency. Carnot efficiency or maximal efficiency, it will be what? It will be TH minus TL over TH. And depending on what TL is, what you see how it is, it will be 20%, 40%, and 60%. And then I compare it. And if my efficiency is less, it's okay, it's possible. It's possible I deal with irreversible cycle. If occasionally they are equal, I say, okay, it's theoretically possible, and my system operates reversible. Finally, if I get like this, it means that it's impossible. Do you understand? That it is. So that's what I do. I find my efficiency, which easily give me 0.4. And then I will look for thermal efficiency, which is maximal. How to calculate it? It depends what I have. My maximal efficiency is TH minus TL over TH. So if I have 200, it gives me 0.6. So what conclusion I make from here? What conclusion I can make from here? I recall this is TH, this is TL, and this is my heat engine here. So my oven heat engine that I have, it has this efficiency, we discussed it. And here I have Carnot ideal cycle, maximal efficiency here. So what is maximal efficiency of this one? It will be this. So what is my conclusion? My conclusion will be it's okay. So it's irreversible and possible. If my efficiency is 40% and maximal is 60, then it's possible. Now, but what happens if I have case B? If my TL is not 300 by 200, then my efficiency is 40%. What does it mean? It means that I operate here reversibly. Finally, what happens if my efficiency is 0.2? My efficiency is 0.4, but maximal efficiency will be 0.2. From here, I will conclude that it's impossible. It's impossible because my efficiency is 40%, but maximal efficiency that I can attain according to second law, it's 20%. So it's impossible. Not because I don't know how to do it, but because it's impossible. So when you read some, let's assume you read some proposal which say my efficiency will be 50%. Right? Let's say you read and say it's 50%. And what should you do to check it? You may go through all details, but find Carnot efficiency for this setup. And if your Carnot efficiency will be 55%, then, well, you may open it and start reading because you can say nothing at this point. If Carnot efficiency will be the same 50%, what you can say? You say, I will not invest money in this because it's a idealized cycle, but you cannot decline it. Potentially this may happen. But if maximal efficiency is 45%, then you say, I don't want to read it, it's garbage. Remove it because it violates second law. Something is wrong there, I don't care why. It's wrong. Do you understand this point? That's what you should do, that's analysis you do. You compare eta, what you do here, you compare eta and eta maximal, right, and see. Again, please realize here, this is still like semi-quantitative analysis, like semi-quantitative. Why semi-quantitative? Because we still don't say how far from ideality. So if your maximal efficiency is 60%, and your efficiency is 55, you say it's reversible. And if your efficiency is 59.5, it's reversible. And if your efficiency is 5%, it's irreversible. And if your efficiency is 59.999, it's still possible and irreversible. You don't distinguish these cases. Key point, it should be less. How less, you don't know. The same story oppositely. If your efficiency is maximal efficiency is 60%, but your calculations give you 60.001, again, it's impossible. And if your calculations give me 90%, again, it's impossible. It does not matter how far, just larger or smaller. Do you understand this? That's what's going on. And from here now, it gives you one more hint when you solve the problem. So you have equations like this. If you know less terms, but if it's stated it's Carnot cycle, then you should be able to compare it. Then you should be able to combine it. Does it make sense for you? Do you understand? Now, that's how we solve this problem. And now, I don't want to waste more time, but do you realize that if I deal with heat pump cycle and refrigeration cycle, it will be opposite scenario. And I can derive the same efficiency. So do you understand that maximal efficiency for refrigeration cycle will be like this? And maximal efficiency for heat pump cycle will be like this. Instead of Q, you write T. Do you understand? And this efficiency will be larger than whatever you have. That's a must. That's what you should realize. Excellent. Do you understand it? So now, from here you will see, I will, yeah, I have almost 50 minutes, I will stop at this point. I just want to open like files that I'm going to send to you. That is summary of chapter 6, because now, yeah, we will do some examples on Monday, we still have some time, but now you should be ready to do everything in your homework. And I do recommend that this weekend you are doing this, because you are ready to do it. And on Monday, I will solve some more examples and discuss, you will have help sessions. So what you should clarify? We talk in chapter 6 about thermal efficiencies for power cycles, and you talk about coefficient of performance for refrigeration and heat pump cycles. You know the formulas, how they look like. These are the formulas for coefficient of performance for efficiencies. And here you have a formula for maximal efficiencies and maximal coefficient of performance. And what is your task to do? It task to calculate this one and this and compare. If your parameter is less than maximal, then it's irreversible. It may occur in practice. That's what typically happens. If your parameter is equal to maximal, it means that you deal with reversible cycles. Theoretically, it's possible. If your parameter, let it be eta, beta, or gamma, it does not matter, is larger than maximal, it's impossible. It violates second. And I request you to remember Carnot cycle. Thank you, guys. I stop at this point, but I'm ready to answer all your questions. And I do tell you, please do your homework this weekend. It's better, so on Monday we can discuss and address your questions. Your homework will be due Wednesday, right?